Hello, my name is Jared Oliver, and I'll be taking you through my thermal energy storage project. And as an introduction, thermal energy storage is by no means new, and it's not really rocket science. It's actually more of, in this case, assisting people do rocket science. And what I mean by that is NASA's Kennedy Space Center, they currently utilized a thermal energy storage system, and it's projected to save them around $260,000 to $300,000 a year in electrical cost at their center, and it's expected to pay for itself in a very long 12 to 14 years. The whole entire reason I'm talking about this is that 12 to 14 years seemed very long compared to other thermal energy storage systems that, for whatever reason, were very low. So I kind of dug in a little deeper, and I noticed that they're using water and they're keeping it below the 40-degree mark, but they're not freezing it. And I'm going to try to make the point that by excluding the fusion of water to ice, there exists a large missed opportunity to save a significant amount of space. I think if they're doing the right thing by trying to reduce their demand, which will also show, but they really need to be freezing this, which I'm sure they have their own reason that I don't really know, but they may not be able to disclose that. Alright, so from this graph we can see that exists this portion right over here that's called the latent heat of fusion, and this property is going to allow us to store a lot more than just the regular temperature differential with a specific heat would be able to. So to prove this point, we're going to take benzene, which has a lower specific heat than water right here at 4.2 compared to 1.7 for benzene, and we're going to have a less intense temperature differential for benzene, and we're going to allow water with a higher specific heat to have a higher temperature differential. Okay, and as you can see, energy required to cool the water 5 degrees is roughly 21 kilojoules per kilogram, and the energy required to cool and freeze benzene, just 4.5 degrees Celsius, is a lot more than 21 kilojoules per kilogram. It's 135 kilojoules per kilogram, and it wasn't able to do this by just a specific heat alone. It had this latent heat of fusion that we showed you from the graph right here. It experienced this, whereas the water, is just doing this. So as a result, it inevitably was able to store or release a lot more energy than what the water was able to. So we're going to look at a case study and the current cooling systems of this university campus, which we're not going to name. It has two 1,300-ton chillers and two 1,500-ton chillers, and these chillers, they're designed to have a maximum inlet temperature of 50 degrees Fahrenheit and an outlet temperature of 42 degrees Fahrenheit, which they never really run them at that unless it's either really hot or really cold, but hopefully I just don't ever have to deal with that. Alright, and we're going to determine the cooling loads from this facility so that we can size the storage tanks and the equipment for the cooling system. And to do that, we need to know what the load is. And luckily the facility at the university campus, they have been logging their data for about 2 weeks. And this data, while I'm very happy to have it, it's unfortunately in the low load time of the year. And it's not really going to be a good indicator of the, hotter times of the year, such as July, but that's okay. We can always revisit that. And if we can determine the flow rate going into the chiller, which we have, and the inlet and outlet temperatures, which we also have, we can calculate the amount of heat transfer going through the chillers. And we can do this with this equation right here. It's the chiller heat transfer, and we're going to go calculate that by the mass flow rate times the specific heat of the liquid, in this case water, times the inlet temperature minus the outlet temperature. And we're going to calculate the electrical power input by looking at the chiller load efficiency, which we kind of have from Train, and the chiller heat transfer, which we are going to be able to calculate. And we're going to be able to see this right here. Alright, so this is what it looks like whenever you do this. You see throughout the day it gets hotter, it gets colder, it gets hotter and colder, hotter, colder, and it'll keep on doing this throughout the month. And this isn't really quite ideal because this is you're not going to get charged on your electric bill for your average demand, which would be that. You're going to get charged for this right here. So whenever they charge you for on-peak or off-peak maximum demand, you only get billed for this one time that you got up here. So that's something to keep in mind, and that's how this is going to save us money, which thermal energy storage in the form of ice is commonly used to lower facilities' electrical demands from cooling by lowering the electrical demands Facilities can lower the cost they incur on their electrical bill. Lowering the demand from cooling can save facilities large amounts of money while also allowing them to have less expensive chillers, which we're going to show you. Which, let's also take a look at this right here, because I may not hit this too good. Alright, so on peak demand, this facility is getting charged $8.63 per kilowatt of on peak demand, plus, and this keyword plus, $4.74 per kilowatt per month of the maximum billing demands. That's really going to be hitting you with that plus. Also, these demands have been changed. They're not the actual rates of the facility. Alright, so here you can see, and notice that this says kilowatts now. This is our electrical power, not our heat transfer. You're going to be getting charged for this time right here. So this is going to be on your maximum peak demand, and your whole entire bill will reflect that. And what we can do to make sure that you don't experience this tragedy of an electric bill right here, we can do load leveling. It's a common strategy, and what we're going to do is we're just going to run our chillers at a constant rate 24/7. So instead of getting up to all the way to this 1200 kilowatts, you're going to be running all the time down here at 425-ish. I guess that's what it is. It's kind of hard to tell. Anyways, so you can just look at that by inspection. You can see that we reduced it about, that's pretty, it's about 600 or, 800, I'd say. Yeah, we'll go with 800. Alright, load shifting is also another one that we can utilize. It is going to be a little bit different. We're going to combine what we just said with a constant rate, and we're going to do that exclusively on the off-peak hours. And not all facilities have on and off-peak, but if your facility does, this is definitely going to be the way to save money. So as you can see here, we're cooling, we're building up ice and meeting our needs. And then we just run the ice right here. And what's this going to cause is you to get charged $0 for the on-peak power demand. And we'll look at that here in just a second, but let's give you a little bit closer look at some of these days. So this is what you'd see on a typical day. We get up, and this is going to be our on-peak and off-peak because it occurs between the on-peak hours. And you're going to see that on your bill. And if we run at a constant rate, you're going to reduce it by that much. So that's quite a bit, which we'll show you later here in just a second. And here is the power shifting. If we move it over, we're going to get charged this for the off-peak and 0 for the on-peak. And here's all together. And this is kind of important. It's not going to raise up your energy used. They're going to be all the same. The area under the curve is the same for all these. So we're going to show you that load shifting will save you the most money. You can see the current system for just that one day was $7,000 for the demand. And the load leveling will be $5,500, which, that is an improvement. $1,000 and $500 is an improvement. Which the load shifting, it made that improvement even better just by avoiding this $8.63 per kilowatt, that's pretty significant, especially if you're still timing it by $4.74. So you can see if we do this for the whole entire 2-week span, we're getting $13,000 for the first one, $6,000 for the second, and only $2,800 for the last one. So if you're getting charged on peak and off peak, definitely would go with this $2,800 for sure. All right, so that slide's just saying pretty much the same thing I just said. The load shifting is going to allow you to ride this money wave. But there is a catch, and it's how much storage you're going to have to be able to do this. Alright, so we're going to calculate that really quick. Alright, so we used about 22,450 kilowatt hours during the on-peak of March 29th, which happens to be our worst day, so that's probably going to be the best day to use for this. So we're going to take that total amount of energy, and we're going to divide that by the latent heat of fusion of ice. It's going to give us that number right there of ice that we need. We're going to take the density of ice, and then we're going to get that volume. We're going to times that volume by a conversion factor of gallons, because a lot of people like to use gallons in this industry. And we're going to get about 70,000 gallons that we're going to need, which not everywhere may be able to have 70,000 gallons of ice, but it is what it is if you want to try and save the demand. So finally, if there exists a decent amount of extra space and you have the funds available, thermal energy storage will serve whoever uses it very well and at a very low cost. All right, thank you.